currently serves as the Chief of Farrier Services in the Equine Podiatry Service at the Veterinary Teaching Hospital at Virginia Tech. He is also a fellow of the Worshipful Company of Farriers, as well as certified journeyman farrier who holds also a therapeutic endorsement and an educator endorsement from the association. He is also your American Farriers Association president. Please welcome Travis Burns.
Thanks, Tom. All right, thank you all for joining me. I know it'd be really easy to be having lunch or out at the bar by now. But thanks for everybody for coming for all of the convention, but importantly, thanks for coming today. So what I'd like to talk to you about is a project where we evaluated the mechanical properties of common composites that are used to repair hoof wall cracks or fractures. So when I talk about hoof wall cracks or fractures, I'm specifically referring to both quarter cracks and toe cracks. I will admit I tend to call them fractures more so to convey a message to the owners. Sometimes, often as owners, they get this feeling when you talk about cracks or cracks within the hoof capsule that they're not a serious thing. Yet it's something they can overlook. But typically, I've found with owners using the word hoof wall fracture kind of displays or gives them a different perception. They can understand more of the severity of it. And so, obviously, the hoof wall is the main load-bearing structure of the horse's foot, and loss of structural integrity of the hoof wall or hoof wall fractures usually results in a marked lameness. And then obviously hoof wall cracks or fractures are usually associated with hoof imbalances, whether that be medial or lateral, or dorsal palmar, meaning long toe, flared toe, dish toes, those kind of things. And they're almost always associated with some sort of conformational fault within the horse. So you obviously have the base wide horse is going to overload the medial side. It's going to be more prone to shunting up, more prone to a medial quarter crack. Same thing, fetlock varus, fetlock valgus. All those things overload a different portion of the hoof. And I found throughout history, obviously those things can be very difficult to treat, and really the key is preventing them from reoccurring. And so when we look at the horse's hoof wall, here's just a cut, just a specimen from it. So from the outside here, you can see up at the top of the screen, that's your pigmented stratomedium, then it goes through the non-pigmented stratomedium. You've got lamellae, dermis, and then the distal phalanx itself. And so the hoof wall itself is designed to prevent microfractures from becoming big fractures. So just the sheer nature of a hoof wall crack, it often will change shape as it comes through the hoof wall. It's very rare, if never, to see a crack that's just like a perfect split through it. They often zigzag in this way and this way, up and down the hoof wall, through the different gradients, through the just due to the anatomical structure or anatomical differences between pigmented stratomedium, non-pigmented stratomedium, inside or outside the most abaxial edge of the pigmented stratomedium to even the most axial edge of the pigmented stratomedium. There's a marked change in anatomical variation through them to prevent big cracks little cracks from becoming big cracks, really. And that's why you'll get this zigzag appearance through it. So anybody that's ever debrided a toe crack or a quarter crack, it's not just one nice clean cut. You've got to follow it through the wall. And so, moving on again, we'd be remiss to talk about hoof wall cracks and fractures without talking about the principles of fixing them. So obviously it's really easy to focus on just the patch or what you're going to put or plate over a hoof wall crack with. And naturally that was the specific part of the treatment philosophy in which this project was aimed at getting data for and coming up with an answer for you. But we'd be remiss not to talk about the entire treatment principles for them. So those are obviously to correct the imbalance as best as you possibly can. Again, based on the horse's conformational defects, you may not ever be able to get them, perfectly into ideal, but, fix them as best as you possibly can. Then we obviously debride the crack back to as healthy appearing margin as we possibly can, getting rid of as many microbes in that area as we possibly can, and then treat the crack with some sort of topical antiseptic to kill the last remaining microbes before you ever cover it or plate it with any sort of the polymethyl methacrylates or urethanes or any of those things. So we'd like to treat them topically, and then we're going to focus on stabilizing the crack, which is obviously kind of the aim of this particular lecture is talking about some of the repair materials that we do use to stabilize the crack. And then we want to support the digit, meaning that we want to try to limit distal displacement of the distal phalanx within the hoof capsule, because as the bony column moves up and down within the hoof capsule, it will pull on the inside of the crack as well as the bones move up and down. And then we have to be committed to follow up. So naturally, obviously, horses with hoof wall fractures or cracks, we often see them on shorter cycles, maintain their balance as best we can, give them less time to grow out of medial lateral balance or put extra stress onto the hoof capsule itself. So first thing we want to talk about are quarter cracks. So this is just a picture of a common quarter crack that we see. Obviously, someone's been trying to treat it with a patch screwed to it, a shoe with a spider plate. So again, trying to achieve some of the principles in treatment, but obviously it's not working. But quarter cracks and toe cracks are quite different, so it's important to remember the hoof mechanics. So here we just have, again, a little schematic. So remembering that a hoof wall is an incomplete truncated cone, meaning that it's smaller at the top than it is at the bottom, and so it's open in the back. And so it's specifically designed for the horse's hoof wall, and the bony column ascends within the hoof capsule. It pulls on the dorsal front of the hoof wall, and then the heels are allowed to expand. So that's normal hoof wall function. The proximal edge and the distal edge and the heel region should both go in and out upon load. And when you get into some conformations, particularly something like this, whether they're angular limb deformities, rotational limb deformities, or they're just like my simple drawing here, which is a base narrow horse. So a base narrow horse is obviously going to put more load on the outside of the hoof wall. We all know as farriers what's going to happen. The medial side of the hoof wall is going to flare. The lateral side is going to want to become more upright. And once you get to a point where they look like this, which is not shown up there. So we have something that happens. So again, this is our base, base narrow horse. So the lateral side, again, becomes pretty vertical, and unfortunately that equilibrium changes, and you have the top, the bony column descends within the hoof capsule, the top's pulled down and in, blows out the medial side, and the bottom can often come in. And all you're doing is essentially just taking a straw and doing this. It's sooner or later it's going to pop. There's only so many times you can move it, and hoof wall is a similar philosophy. I know that's kind of a crude little metaphor to think about snapping a little windy straw, but that's all that's really happening to the horn tubules of the hoof wall. So again, it's important and paramount to correct that first and foremost. So if you correct or compensate for that, you can do a lot of things when it comes to patching or just trying to stabilize the crack or the defect. So this often obviously leads to a medial-lateral imbalance or improper or less than ideal placement of the distal phalanx within the hoof capsule. So 0-degree dorsal palmar radiographs centered at the dorsodistal margin of the distal phalanx gives you a nice view to guide medial lateral balance. And so if we just draw a line on our base, wherever it is, and compare the angle of the distal phalanx within the hoof capsule, obviously we're trying, again, most ideal would be to get the distal phalanx or the distal margin of the distal phalanx parallel to the ground, or as parallel as you can safely for that horse based on its conformation. But we looked at the drawings, but this is obviously what they look like in real life. And so we also want to improve or increase their base support. So first thing we're going to do is trim them to try to provide for medial lateral balance. And then when you look at them from the outside, again, you can see the top of the wall comes down at one angle, and then you can see the bow in it. So right there is where it'd be prone to quarter cracking, right at the junction of that yellow and blue. So everything's going to want to come out there. It's why most of you have seen a quarter crack pop, in real time. It usually happens about 1.5 centimeters, 2 centimeters down the wall, and then propagates proximally and distally. They don't really crack at the cornet and then propagate distally. They pop in the middle, and it's usually right around this junction. So one of the big principles we have with it is providing the appropriate base of support. So extending that line down and fitting a shoe in that model as best as we can to try to recruit or get as uniform growth or correct for the imbalances that we have within the hoof capsule. So just like I said, we keep moving through the principles of treatment. The next up is to debride the crack. Obviously many different ways to do that. You can do it with motorized sanding tools like this, a Dremel. You can do them with loop knives, bone curettes, whatever you use to do it. We have found, or at least in my practice, the thing I like the most is a Dremel, and I really prefer this bit. And so obviously I don't work for burrsforless.com, but it's a wonderful place to find these little double cross-cut carbide burrs. And they do a couple things that I think make up for the drum sanders, those little tungsten bits. So all of those create a lot of dust and a lot of heat. So these things cut and will literally throw hoof wall out of your sight. Not that it's all that important, but you would absolutely want to visualize it as best you can. So this prevents dust buildup in it, and it prevents heat buildup in it. So again, I think, from what I found, this is by far and away my favorite tool. And so if we go back, you can see the debridement, how specific it is, and how precise you can be. And you can get them in a couple of different sizes. You can get them even markedly smaller, because we all know when you're debriding and trying to get to as healthy a margin as you can, you do get right down to the junction between, stratum internum and the non-pigmented stratum medium. And right at that junction is when you'll get some capillary ooze or some mild hemorrhaging. And we all know when you're patching cracks or gluing over top of those things, you're just asking for trouble. So we'd like to prevent that or keep that from happening. So the debridement must be as precise as you possibly can. And certainly these bits and tools allow us to do so. So just going through, talking to you about the, kind of iron method. Again, I'd be remiss not to tell you how we patch or how we plate quarter cracks, and then talk to you about how we, or what we wanted to test. So essentially what we do is take any of the polymeric fabrics out there, saturate them with a polymethyl methacrylate, which in this case for us is most commonly Equilox, and then we use however many layers of it and plate over it that we want to. Okay, and so any of the polymeric fabrics, again, clinically or anecdotally seem to work quite well. So in the upper left-hand corner there we have matrix. So it's just again, Curtis would never tell me exactly what that cloth is, but it's a nice, not very abrasive resistant fabric. It's very easy to rasp, clean up, looks good, but it's not very abrasive resistant. We have polyester Vectran in the upper right. It's extremely abrasive resistant. You can't really rasp it once it goes on. It's quite difficult to cut. Down at the bottom we have the rest of them. So we've got polyester Vectran is the big one on the right. That yellow and black one is called Cobra Socks. So it's a carbon fiber Kevlar mix. What else is there? Fiberglass is the one you see right up front, the big square. So that's just traditional fiberglass from Equilox. So again, it's very easy to cut. It's not very abrasive resistant, but does beautifully. You can rasp it, blend it, and make it look really nice. And then behind that, I believe we have the old-fashioned one, Spectra. So again, Spectra was really hard to cut, but it's similar to fiberglass in that you can rasp it and make it look quite nice. Okay, and so again, for the plating technique or using these fabrics and polymethyl methacrylates to stabilize the crack, it's just like gluing on a shoe. So the first step is to prep the hoof to accept the adhesive. So whether you use a hoof buffer, a rasp, a sanding sponge, one of the finishing systems, anything, the goal is to remove all the dirt and debris from the outer hoof wall and any oils from the area. So proper prep is important for the adhesives to stick and adhere to the hoof wall. So from there, again, I would tell you if you're patching a crack for the first time and probably really all the time, if you're going to use a plating technique, it's open top and bottom, so it can remain treated. It doesn't become an anaerobic environment unless a whole bunch of dirt and debris packed in that area. So we use any number of things. So this is just a picture of a piece of weather stripping in there. You can take white medical tape, roll it up with the adhesive side out, stick it in there. The heat from the glue kind of melts it, and you can just pull it right out. You can use impression material, a 4x4 soaked in Furazone, any number of things to keep glue away. But the basic principle, whatever you put in there, is to keep glue from getting to the depths of your crack. Because if you debride a crack, there's no doubt to your eye it's probably a healthy appearing margin, but there's still microbes there. And you seal them up or close them up, you're just playing with fire and asking for an abscess. So we like to keep glue away from the most axial edge of the crack or fracture defect. Okay, so from there, we just secure it or whatever we put in there, and also protect the cornet. So I like to use just electrical tape. It seems to work really well for me and leaves a nice clean border at the top. So you can put it on, and when you put it on, I like to put it on at the exact angle of the hoof wall. So when you put the plate on, everything looks parallel. It just looks nice when you do it. But really all it's doing is there to protect the cornet. So you just take whatever polymethyl methacrylate you choose to use, from Equilox, Grand Circuit, Equibond, they're all pretty much the same, just a two-part mixture. You put in a cup, stir it up. This one has dye added to it just to make it black. But you want to stir for 45 minutes to an hour, or not 45 seconds to a minute. If you want to stir for that long, I don't know, maybe you should be a baker or something. But 45 seconds to an hour, 45 seconds to a minute. Okay, and that is something you don't want to skimp on. So it's easy when you're not comfortable with the polymethyl methacrylates to want to just stir really quick and get on with it. But what happens is you don't get a nice mixture through it, and then you have these weak spots in whatever you're trying to provide structure to the hoof capsule with. So you really want to make sure you get a nice homogeneous mixture with it. So it's really, really easy when you have the dye, because obviously you've got something black and something white. So it's really easy to make sure you're mixed up. But when you just have just the beige and white, it's not uncommon to not get a nice good mixture. So you should stir all sorts of directions within your cup, flip it over, turn them over, do all kinds of things to make sure you get it as mixed as equally as you can, or use the mixing straws. Just remember to waste the first part that comes out as it's not mixed. But I like to just do it in a cup. And then from there, we just take your fabric, however many layers you decide to use. I just literally do it in my palm. You can lay out plastic wrap on a table. You can do whatever makes you comfortable. But I just take the fabric, put it in my hand, spread Equilox or polymethyl methacrylate over the entire area, and then I fold it. So you can cut them in specific layers and then try to stack them. But I found it's really hard to make nice, clean edges, so I just like to fold it. So if you take, a 4-inch piece, you can fold it into thirds and have 3 layers, fold it in half, and have 6 layers in a nice little square in a nice little rectangle with no frayed edges. Makes for a nice pretty patch. So we're going to saturate the fabric all the way through. Again, you can see this is how I just folded it over in my hand. And it is important, whichever hand you've got it in, you should probably have 2 gloves on the hand that you're putting glue on with. So you keep it in this hand, this becomes your working hand. So you smear the glue, take your thumb, shuck the glove, then the other glove's still there and your hand's clean. You can pick up the foot and go straight to the foot without fumbling around or having 5 people there to help you or putting a big black paw print of polymethyl methacrylate on a pretty white horse. It usually doesn't go well. But we take it and just fold it into a nice little rectangle, into a nice little plate. So this particular one is, you can see, it looks like matrix, 3 layers of it, and then you take it and just put it on the foot again, right over top of the whatever you put in there to keep the glue from getting to the most axial edge of the crack defect. But here you can see this is why I like to put the electric tape on a very specific manner. So then you put the plate on and the same thing, and it all will come out looking pretty parallel and fairly clean. So from there, then we're just going to wrap it with whatever plastic wrap you have. Wrap it up nice and tight. It does a couple things. It keeps the heat in. It presses the glue down within the composite material. And then from there, you'll take it and actually use a knife, the handle of the wrap, the roll of wrap itself, anything to roll it and smooth it. So your goal is to remove as much excess glue as you can. So glue is actually your weakest part within it. So if you have these unlevel areas or bulges or anything within the plate or the fabric, unless it's perfectly smooth and uniform all the way through, you have weak spots. So if you put a big air bubble in it, or you have just a big blob of glue in it, and it looks like this, you're just asking it to fail here, here, or here. Okay, so you're wanting it to be one nice smooth arc and have as little glue in there as possible. The fabric is actually the strongest part of it. That's what we're going for while trying to stabilize the hoof wall itself. So you wrap it up, press it flat, make it look nice. You can see where the excess glue goes, up, down, and in front of it. And so then you can pull out, you know, this little weather stripping, it works very easy just to pull out, leave yourself a nice little drain. You can see it from the bottom. There's a nice little hole. You can treat it from the top, just let it drain down with whatever topical treatment you like, from tincture of iodine to thrush buster or whatever you guys feel comfortable putting in that defect. And then this, you just take a rasp and just clean up all the edges, and it makes for a nice little plate on the outside of it. And then there's any number of variations of them. So again, you can have, this one's just 3 layers on this side with a glue-on shoe. That one's got 6 layers with a normal nail-on shoe. You know, 8 layers plus the 2 layers from the glue-on shoe. Those are all what I call plating, meaning they're that nice little rectangle, meaning it's open top to bottom. And the bottom, you can also, again, like I said, some people like to just rebuild the whole heel. So you just cut out triangles, and you can, again, still in the fabric itself, cut the triangles, just like we used to do the little paper snowmen. You pull them out, you can fold them up, cut it, and then just fold them back, and you won't have really that many frayed edges. And so again, I know that's a lot focusing on the patch itself, but really that's the objective of this study, is to evaluate those composites. So I would be remiss again to tell you not all quarter cracks need to be patched, right? So obviously I just went through a whole lot on how to patch quarter cracks, but very, very commonly if you correct the medial-lateral imbalances, if you stop what is the cause or the predisposing factor for the quarter crack, they often just grow out, right? So quarter cracks are fairly easy to treat for those of you who have done it, where toe cracks are a totally different animal, right? So these, in my opinion, are, oh God, went on. So again, like I said, I probably don't patch all my quarter cracks, so just like we were talking about, they often grow out if you just fix whatever is causing the quarter crack. But again, toe cracks are a totally different animal. So when we start talking about toe cracks that look like this, we have to remember that the hoof wall behaves quite differently in that area. And so when the foot loads, these very much scissor close at the top. You can even see at the most proximal edge of this horse's hoof wall how it is truly overlapped at it. Okay? And then the bottom will want to open. So there's a lot of movement when the entire dorsal hoof wall fractures mid-sagittal. That you truly do have 2 independent halves of the hoof wall, and very characteristic things happen. So even though this horse has a shoe on, has a shoe with clips on, you can still see on either side of it how it bells out, it flares out. This is true loss or destabilization of the hoof capsule. And so when we talk about then the forces that act upon them, the entire bony column and the horse loads, descends within the hoof capsule. Plus you have pull the deep digital flexor tendon on it all the time. So the front is the bony column comes down, the deep pulls on it, the dorsal hoof wall comes down and in, the outer hoof wall at the distal aspect of it kind of flares and will open on either side. So when you look at a medial-lateral view of it, of course you're going to see exactly what you would expect to see, right? You've got a lot of dishing in the toe area. You've got a big long toe lever there. And again, I'd be remiss to talk to you about patching or plating these cracks without talking to you about the principles of Farrier to correct that defect as well. Okay? And so when we talk about toe cracks, you're remiss again not to use radiographs to guide your trimming and shoeing protocol. So you can look at it. Obviously this horse has some issues. When you look at it, if you just look at the horse's base of support, so you can argue over where exactly this is, but roughly the center of rotation of the distal interphalangeal joint. I feel like everybody, regardless of the principle, can all agree we'd like to have a shoe or a base of support half in front of it or half behind, somewhere close to that point. And so in reality, in my mind, when I look at them, I don't measure these down to the millimeter and lose a lot of sleep over it at night. I just look at it as a lot or a little, and it has a lot of lever out in front of it and very little base of support. It doesn't really matter to me what the number is, just that ratio just has to get fixed to start addressing the toe crack or limiting the predisposing factor for the toe crack. So again, be remiss not to show you what we do entirely. So this lateral medial radiograph, you can see a couple things. You see the base of support is markedly improved, closer to 50-50. Everything's moved back. You do, in these cases, want to require or maintain as much sole depth as you possibly can. Again, not that you want to have a 4-inch long foot, but you would like to have sole depth to be able to dress the dorsal hoof wall back. If you don't have sole depth, you can't just hammer or dress back the dorsal hoof wall without creating a marked lameness. So you see a couple things. We dress back the dorsal hoof wall. You can already tell, I'm sure those of you that are used to seeing radiographs, that there's some sort of patching material on the outside of the hoof wall. Hopefully everybody can see that out in this area. And then inside, you can see this faint white line, right? So that's the true depth of the crack itself. So after it's treated with a topical thing, so on this side, I can't see the thing. But anyway, if you look at the dorsal surface of the distal phalanx, there's a bright white line, abaxial to it. And that shows the depth of the crack from where we've been treating it with 7% tincture of iodine. It's radio opaque and shows up. So it's a nice way to show you the true depth of the crack. So this is a true full thickness hoof wall crack or fracture that extends approximately distally the entire length of the horse's hoof wall. And so again, creating, fixing the horse's base of support is first and foremost. Secondary from there, provide some sort of frog and sole support. So again, doesn't matter to me how you get there or what you do. The big principle is you just want to recruit as much of the frog and sole into load bearing as you can to limit, up and down movement or up and down tug on the hoof wall crack or fracture itself. So hard bars with pads, Equipack, frog pads, flat pads, whatever you use. The idea is to take some of the stress and strain away from the dorsal hoof wall and recruit the frog and sole into load bearing. So from there, again, just like the quarter crack, we're going to debride that. For this one, obviously, we're going to dress it back. So you see the differences in the hoof wall down at the very bottom. So it's been dressed all the way through to the white line, really, to where you have those old epidermal lamellae down at the bottom. So it's dressed back, again, to try to match the angle of the dorsal surface of the horse's hoof wall. So that's the first thing you see. And so you can see down at the bottom the little Equipack pieces on the outside. So even prior to plating or patching this crack, we had the owner bandage the foot and treat it topically for 7 to 14 days just to reduce microbial content within the crack bed itself. But even while the horse is being bandaged, you can still recruit the frog and sole into load bearing. So we just squirted in some Equipack and left it there for the owner to keep bandaged in, even for those 7 to 10 days. And then from there, you obviously have, I guess I should have showed you. So that's what I was talking about. So you see the Equipack down at the bottom. It's being treated with tincture of iodine. And again, this was just bandaged like this for 7 to 10 days. Because when you have a crack that goes all the way top to bottom like this, you probably end up patching more of the hoof wall and not really have that true aerobic environment behind it. So just to reduce the risk of abscessation behind our repair material, we have had the owner treat it for, I honestly can't remember, 7 to 14 days, I'm sure. So from there, you have any number of just like the quarter cracks, patching or plating techniques. So again, these are some of the same repair materials, just the one's just purple dye, a kid horse, and they like purple. But these are like, each one of those are probably 6 to 8 layers of polyester Vectran put over them. And I will tell you, in my life and career, what actually prompted or started this project, which at this time I would like to say was funded mostly or in part mostly by the AFA Equine Research Fund. So thank you guys very much for doing that. And then from there, what I noticed is oftentimes to get this crack to stabilize and get to that foot, the repair composites with the fabrics weren't always strong enough. So again, the quarter crack is not to sound arrogant or something, but they're often easy to fix. They're not that bad. But these toe cracks are oftentimes really, really hard to get that first, quarter to a half inch to grow down and be solid. These are very easy to keep recracking and repropagating. And so I often found that patches even like this with multiple layers all the way top to bottom would still recrack. So I found myself with toe cracks, getting them to grow out, often having to do something like this. So reinforce it with brass or aluminum or steel or something at the most proximal edge of it. And so naturally that's what prompted this study. And so the objective of the study was to determine the mechanical properties when we think about the the three forces that act on the hoof wall and the hoof wall crack itself, meaning tension, bend, and compression. And then test the four composites most commonly used to repair these cracks, at least in my practice. Okay? So, what's next? So again, in the introduction, I probably went mostly through that for you guys, but obviously the three main forces that act on the hoof wall are tension, meaning it's opening, the hoof wall is being pulled apart. Compression, obviously that the hoof wall at the toe, when I showed you they scissor closed, that's compression. And then bend, meaning that it comes down and in when the distal phalanx sinks within the hoof capsule and the wall bends in this plane. So all three forces act on these toe cracks. And again, the hoof wall fractures or cracks result in the loss of structural integrity within the hoof capsule. Obviously, they only heal by replacement by growth. They only heal from top to bottom. They don't just all of a sudden start growing in and out. But obviously, you guys know that. And frequently, we as vets, farriers, practitioners, when we're faced with these, oftentimes we have to find some way to stabilize them for the horses to keep going. Okay? And then again, the most common treatment for us is a plating technique with one of those composites saturated with PMMA. But in reality, when again, people would ask me, why do you choose which fabric? I would often tell you it just came down to whatever I thought was prettiest. There's no scientific evidence out there supporting, the use of fiberglass or Cobra socks or polyester Vectran, any of those things. So we aimed for this study to be able to allow the practitioners or the vets and farriers to be able to make informed decisions on which composite or repair material they want to use. So the first part of the study was to test these composites in tension. So we took these pieces, made them 8.5 inches long. They're a 1/2 inch wide, and then in the middle where they're kind of dog boned or recessed, they go all the way down to 1/4 inch. And so that's designed to know exactly where they're going to fracture and fail. And then from that point, we took I guess I would be remiss to tell you, there are the 4 layers there. So all the way out on your right is matrix coming towards me, or to the left-hand side would be matrix, fiberglass, Cobra socks, polyester Vectran. Okay, and so they're dog bone in the middle, so when you put them in these Instrons or universal testing machines, they're designed to fail in that spot. So you know where to put your extensometer to measure the stress and strain or the deformation in that area. So essentially what this thing does is very controlled and will just pull them apart. So the very slow thing. So to break one of these apart, I forget exactly how quick we set the cross head moving. I think it was 0.5 millimeter a minute. So it takes quite a while for it to break, but very controlled. And then the extensometer measures the stress and strain in that area. And so when they fracture apart, these are just showing you some of those pieces that fracture apart. So on the left-hand side, top to bottom, you have polyester Vectran and then Cobra socks. And then on the right-hand side, you have matrix and fiberglass. And so these are very specific fracture patterns, and they tell you the structure or the braid of the material itself. So the two of them, polyester Vectran and Cobra socks, are a 45-degree braid. So when you look at how they're braided, you can pull them, they stretch. Where the fiberglass and matrix, they're both 90-degree braids. So the way they're put together, so they have a very specific fracture pattern. And then not that I want to bore you guys with too much information about what it exactly is being measured, but essentially there's a couple things you need to think about. So we're measuring essentially stress over strain, and the stress is essentially just the force that's being put on the repair material by the machine. Okay, and then measuring it over the area in which it acts, so that quarter inch piece. And then the strain is essentially how much it changes in length over time. And then you take those and put them together, and essentially what you have is something called a modulus of elasticity, which is again just the rate of change of strain as a function of stress. And all that does is mean the higher the number, the stiffer the material is. That's all that it means. So it's a big word with a fancy definition, but it's just a measure of stiffness of a given material. Okay, and then there you have yield strength, is the area in which a material goes from elastic to plastic. And again, all that is a fancy definition of telling you when it does not return back to normal. So you can stress something and have it return to normal, or you can stress it and it never returns back to normal. At that point, that's when it changes from being able to go back to normal to not being able to. So for us, when we think about these repair materials and hoof wall, it's that point in which we have failed. So if you, at that point, if you don't have that point be greater than hoof wall, then it's going to fracture the hoof wall beneath it. Okay? So when we look at them, that's what we tested. So in tension, we tested the modulus of elasticity of those 4 composites. Again, to see the modulus of elasticity just tells you how stiff it is. So the higher the number is, the more stiff or more rigid it is. And so all of these for the modulus of elasticity is all greater than what is reported for hoof wall. But again, I really think the tensile yield strength is what we should be looking at, and tensile yield strength of the repair composite should be greater than the ultimate strength of hoof wall. So when we look at ultimate strength of hoof wall, that is when we know for sure it fails. You know, that's the strongest point, that's the most stress you can put on it before it fractures. So if we know the ultimate strength of hoof wall, then we know as long as our yield strength of our repair material is greater than the ultimate strength of hoof wall, it should stabilize the hoof wall or prevent it from fracturing. And so when you look at these numbers and you put in the blue line is what is reported the tensile ultimate strength for hoof wall. Okay? And so when you look at these, only 2 of the composites were greater than hoof wall. Doesn't mean that the other 2 composites won't get it done. It's just if you were trying to make a decision and you wanted to know for sure, I guess you can never say for sure it won't fracture. But if you wanted to give it the best possible reason not to fracture, you would pick a composite that is greater, has greater tensile yield strength than the tensile ultimate strength of hoof wall, which would mean you would select Cobra Sox and PMMA or fiberglass and PMMA. So moving on from there, the next we tested was bend, similar thing. We made our little specimens. They're markedly smaller. They go into the same machine with a different jig, and it pushes down, and the extensometer is put up there. You'll see it on the back side with the rubber band, so it measures the rate of change within the ultimate, or the International Testing Machine, or the Instron machine itself, and it's just tested in a 3-point bend. So again, 8 replicates of each, and all of these were all made with polymethyl methacrylate. They were all rolled with 10 pounds of pressure 3 times, and they were all rolled with 4 layers of each repair material. Forgot to probably tell you guys that. And then from there, again, the results from bending, again, very similar. The modulus of bending, again, just tells you how stiff it is, and they were all greater than hoof wall itself. The hoof wall down at the bottom, what I've got reported is there's a difference in inner wall and outer wall. So pigmented stratomedium, non-pigmented stratomedium, and then there's even a difference on the most axial edge of non-pigmented stratomedium to the most abaxial edge of non-pigmented stratomedium. And so again, if you're thinking about bend, you would want the bend yield strength of your repair material to be greater than that of hoof wall. So again, if you just think about these, the numbers make sense because you can set and bend hoof wall clippings pretty easy. I mean, it's designed to move like this. It's an arc. It's easy to bend it. So, you know, in reality, when you look at the numbers, pretty much all of these repair materials other than Matrix all had a bend yield strength greater than that of hoof wall. And when we think about this one, this is one of the ones that I think this result leads to a lot more questions than answers, for me at least. So when you look at these, how much more do you want to increase it than hoof wall? Or can you repair a hoof wall so much that you limit independent heel movement or heel expansion of the hoof capsule? Can you actually constrict the horse's hoof capsule with a repair material? And that's one of the questions remaining from this study or a result from this study. Is nobody knows how far or how much you need to go, or at what point, what bend yield strength will you, kind of constrict or keep a hoof wall from moving. So the fancy blue line. So again, they all, except for Matrix, got above the realm of the bend yield strength of hoof wall. And then from there, the last portion we studied was compression. So again, it's a jig, so 8 replicates of each one of the repair materials. Again, 4 layers, all made in the exact same way. We're putting a jig, and essentially what the jig does is it holds both ends of the pieces as close as you possibly can, and then the machine pushes this way. And so you'll see something, does specifically happen to these things. So they do delaminate. So you're taking them, you've got layers of polymethyl methacrylate, the fabric, polymethyl methacrylate, fabric, polymethyl methacrylate, fabric around them. So what happens is when you start compressing them, they blow out this way. So they kind of delaminate. And so you'll see as we go through those results, and we look at the modulus of compression, which again just shows how stiff it is. All of them again are stiffer than hoof wall, but unfortunately now you'll see the yield strength is markedly lower than hoof wall. And that's a result of the materials just delaminating. So they're not very strong in compression. And so I really think the compression on the toe crack itself, so the fact that the scissors close so hard, and these repair materials are very difficult to stop or limit that from their delaminating or the stress in which they just take the strain, is again far lower than hoof wall, which is why I think oftentimes we've had to repair them with the metal materials. And so luckily, when we look at them, so again, there's no blue line because they're all lower than hoof wall, so it would be way up there about the light. Okay. So from the bottom, so naturally, it's very, very nice to think, oh, well, we should include the metals and do the exact same things to them, but luckily these very nice students at MIT had already done that with actually the most common things we use to repair hoof wall with. So they did it with 6061 aluminum, brass, mild steel, and so we were able to take their numbers and compare it with hoof wall. And again, hoof wall, like I said, there's a big difference between outer non-pigmented stratomedium and inner pigmented stratomedium, and then even outer non-pigmented stratomedium. They're all quite different, so that's why they're reported in a range. So the yield strength in compression for hoof wall is 220 to 117 megapascals. And from there, if you just look at the graph, again, the aluminum and brass do get into that window. But if you were ever to say, well, I absolutely want to choose something, will definitely get me above that window, steel is the only one, or mild steel that gets above that. Or at least of these materials tested, which I feel like are, it's not reported, but are probably the most common materials used to repair the hoof walls when it comes to metals. And so again, like any project, there's a great deal. So, well, again, I forgot the little blue lines for you guys, but you can see the aluminum and brass get you into the window. But if you really want to go above and beyond and make sure you're above the yield strength of hoof wall, then you would want to use steel. Okay. And then so obviously there, from anything, we're just going to try to look at or make some conclusions. And so again, all composites exhibited a modulus of elasticity greater than what's reported for hoof wall, which indicates these composites are stiffer or more rigid than hoof wall in all directions, meaning tension, compression, and bend. Yet the tension yield strength of fiberglass and Cobra stocks is greater than the ultimate yield strength of hoof wall. The bend yield strength of polyvectran, Cobra stocks, and fiberglass are all greater than the bend yield strength for hoof wall. But unfortunately, compressive yield strength for all of these composites was lower than the compressive yield strength for hoof wall, which again I think is what makes them susceptible when we start repairing toe cracks with them. These composite repair materials may not be strong enough for the toe cracks unless they're reinforced with metals. And again, I really think it's just from the compressive nature of the proximal end of the toe crack. And the results of this three-phase study do enable vets and farriers now to make evidence-based decisions when selecting the appropriate composite for hoof wall fracture repair when looking at these four. But obviously it does lead us to the future and some more future projects or questions. And so again, I'm wondering what these composites would look like if you mix them. So if you had a layer of Cobra stocks, a layer of polyester Vectran, a layer of fiberglass, is there any reason, is there any benefit to combining different repair materials to form a composite? I do know it's reported in the literature some practitioners do like to use, a layer of polyester Vectran, a layer of Cobra stocks, and then a layer of polyester Vectran. But those composites probably do need to be evaluated as well. And again, like I said earlier, can a repair material be too rigid and have negative consequences on the hoof capsule itself? So a great project would be putting a strain gauge on the heel region of a foot, and then repairing one of these plating techniques, and then see what actually happens to heel expansion, both of the proximal end and the distal end. So again, obviously every project leads to future projects. But from there, we just have some further reading for you if you want to. And then at that time, I'll take any questions you guys have. Yep.
Taking into consideration the strength of the bond between the material and the hoof wall, is the material stronger than the adhesive bond of the hoof wall?
Yeah. So the question is, do these numbers matter if they're greater than the force it would take to knock the adhesive off of the hoof wall? And no, that was not tested in this project. So the question is, that brass repair material that was on that hoof wall I showed you, was that attached or screwed to the repair material or the hoof wall, or both? And in reality, I can't remember that specific course to tell you how far it went, but my aim was to only secure it to the repair material itself. So again, my objective was to, it's a little 1/4 inch plate, and I put it on 1/2 inch screws, and then you have a repair material. So my goal is for the screw not to go all the way to the hoof wall, just so we don't run the risk of having a lameness associated with it. But I would be lying to you if I told you sometimes I'd take that repair material off and it is slightly into the hoof wall. But I'll admit on that particular horse alley, I can't remember how I did. But the aim was just for the repair material. So, sure, Diego?
Calculate your tensile strength of the wall.
Okay, so the question is, how was the tensile yield strength of the wall done? And so, I forget which one I put in here for you. Is it from Lay? Oh, this one. All right, so it came from, so that particular paper, what they did was they actually took hoof wall samples that were nipped off the bottom of the hoof wall post-trimming, and they were taken immediately to a mechanical engineering lab. They were cut into uniform size. Naturally, it still has the arc to it, so they weren't cut perfectly rectangular. And then the same thing happened to them. They were put into the instrom and dog bone in the middle to fail. So the exact same things were done with them. But it is important to know that it was at the most distal aspect of it. So when we talk about hoof wall and those numbers I reported to you, it doesn't really take into consideration the lamellar attachment between the hoof wall and the distal phalanx. It's literally just looking at, pigmented, non-pigmented strata medium. It's not looking at or including the lamellar bond as well.
Question over here to the left.
Do you have any guidelines for how many layers, how big the patch?
Yeah, so the question is, do you have a guideline on how many layers or how big the patch should be? And no, I unfortunately do not. So all of those tests have to be done over a specific measured area, and so they weren't compared against larger areas. They're all equalized to give you a number over an area that could be extrapolated, I guess, to a certain degree. But in my mind, that's still one of the things that we do anecdotally. And so for me, again, everybody knows I love Dale Earnhardt, right? So I like 3 layers. Yeah. But there's no really science behind it. But there is, obviously, when you have those repair materials, they're very easy to roll into thirds. And the way they come, they look really nice on hoof wall. It does usually give you a top and bottom pretty well. But you can see in some of those pictures I showed you, some of the cracks scare you more than others. So one had this, a nasty keratoma under it that wasn't surgically removed, and so I had to put 6 layers over it to get it to not propagate further in the quarter region. It wasn't a traditional quarter crack, but most quarter cracks I use 3 layers. Most toe cracks I use 3 big layers, and then 1 folded into thirds across the top, or sometimes double that. So the most I've ever really put on are 3, 3, and 3. So what is that? 9, and then reinforce with a piece of metal. But, yes.
Where are you at in the purity process?
We're not even in purity. We're in manuscript preparation at the moment. Any other questions? Yes.
What's the thickness of the plate? I'm not studying. This is the strength of the plates, but does it say like?
Oh, I'm sorry. So the question is, what is the thickness of the plates in that study? And they were all done with 1/4 inch in rectangles. So, half by 1/4 for the tension and the bend. But the compression for them, their project was quite different than ours, because our repair materials, we really couldn't do it. But they, for their compression tests to get a better, more accurate number, they used cylinders. So they were 1/4 inch diameter. But for us, I couldn't figure out a way to make the repair material be the cylinder. And then even then, I'm not sure it would give you the same data as what is actually clinically applied.
Okay. I'm going to say thank you for multiple things here. Thank you for coming and presenting this for us, for the equine research. And the other thing, hang on. The other thing that it is, this has been our president of this association for the last 2 years. He is a new father, so I'm letting him get out of the job. But I want to say thank you, congratulations, and best wishes as always. Appreciate your service to the association, and I hope these people do too.
Great. Thank you very much.